Next section is going to be covering counting, permutations, and combinations. We're going to go over the counting principle, permutations, combinations, and how all of these connect to probability. The counting principle is a basic way to figure out how many total outcomes are possible when a process happens. You can find that out step by step. Permutations are used when we're arranging items and the order matters. And combinations are used when we're selecting items and the order does not matter. So when we understand these ideas, we can count outcomes efficiently and then use those counts to determine the probability of different events. So let's take a look at our first example on the counting principle. The counting principle is a fairly straightforward concept, and the counting principle basically says we determine all of the possibilities of each possibility type, and then we multiply all of those possibilities. So let's look at this example here. It says Stefano owns a restaurant where his customers create their own pasta. The customer chooses exactly one type of noodle, sauce, vegetable, and meat. And the following table shows the options available to them. And so for the noodles, we have three options. For the sauces, we have three options. For the vegetable options, we have four options. And for the meat options, we have five options. And says how many different pasta dishes can customers create? And so we're going to multiply all of these. And this is how we apply the fundamental accounting principle to find how many different dishes can be made. And this equals 180 when we type that in our calculator. That's all we have to do with this problem. Let's look at the next one. Aula is going on an outdoor expedition with his family. The expedition is going to include a hunting event, fishing event, hiking event, and a camping event. There's 4 hunting, 7 fishing, 6 hiking, and 3 camping events for the family to choose from. How many different expeditions are possible? So we're going to multiply all of these types of events and the number of each type to find the possible expeditions that there are. We're only choosing one of these, but there are this many possibilities if we end up multiplying that, and we should get 504 for our answer. All right, so those are fairly straightforward problems. Let's go to another concept, permutations. So permutations are used when we want to arrange items and the order matters in that arrangement. That means changing the order creates a different outcome. Uh, for example, if we're running a race, finishing first, second, and third place are all different positions. So each arrangement counts separately. So that's what we mean by an arrangement of items, or when we're talking about the order of something, we're running a race, we can get first, second, or third place. So the order that we're uh, coming into the finish line matters. So the goal with permutations is to count how many different ordered arrangements are possible in a given situation. And this idea is especially important when we're doing anything like ranking, scheduling, or organizing anything where position makes a difference. And the formula for permutations, we write it like this. We say NPR. And you can also see that sometimes on a calculator, it looks like this instead. It says P and then it has N comma R. So we can write the numbers like that on a calculator. But the formula for this is N factorial over N minus R factorial. And those parentheses are important. If we don't have the parentheses there, that would just say R factorial. But this is N minus R, whatever that is, and then factorial. So N stands for the total items that are in the set. I'm just going to say total items available. And R is the number of items that we're choosing. Okay, so this problem wants us to figure out what is the N and what is the R. And at first glance, if we just look at the numbers that are in this paragraph, we have more than two numbers. So we have to figure out what is the total set, and then what is it that we're actually selecting from that set. So N is the total, R is what we're selecting from that set. So we have to filter out a lot of extraneous information in this first example. This biology teacher has 5 different pets they keep in their classroom. For an upcoming holiday break, the teacher is going to send the pets home with the students. And it says, suppose that 16 of the teacher's 75 students volunteer to take a pet home. And the teacher will randomly select 5 of those volunteers to each take one pet home. And it says we can use the permutation formula. What is N and R in that formula? So you might at first glance think, oh, there's 75 students, but let's think about what we're selecting. 75 is not what N is. At first glance, it might seem like that because it's the biggest number, but what we're talking about is there are a set of students who are going to select uh, or be selected volunteers to take a pet home. So there are 16 students volunteered to take the pet home. So not all 75 students wanted to take the pet home, just 16 of those students. And then the teacher's going to pick 5 of those 16 students to take the pet home. The 5 different pets, that's not an important part of this problem for just determining N and R. The one pet home also is not important in the problem and the 75 students. And so that's all we have to do for this problem is figure out what is the total items available and what's the number of items that we're choosing. All right, so this next one, actually, let's go back up here and let's calculate what this would be for example 1 before we move to the next problem. So let's use our formula that we wrote up here. 16 factorial over 16 minus 5 factorial. Now, the problem doesn't ask us to do this, but in some other problems, we are going to be using the permutations formula. So it's probably good that we just look at an example sooner rather than later. So when we're writing out factorials, a factorial is we start with the given number, we multiply by the next integer that's below it, and then we continue the pattern. And we would continue this. I'm going to write it until about 10. So times 12 times 11 times 10. And then I'm just going to put dot, dot, dot times 1. And now this is 16 minus 5 factorial. That's 11 factorial. 11 factorial is 11 times 10 times 9. And I'm just going to put dot, dot, dot times 1. Now we can start canceling some of these values out. So the 11 and the 11 cancel, the 10 and the 10, all of these numbers are going to cancel. And so we're just left with this on our numerator. And when we put that in the calculator, we should get 524,160. Okay, so that's how we calculate a permutation, but we'll look at some other examples too. I just wanted to show you that what the factorial means and how we can cancel out those values with this formula. We could also write this formula like 16 times 15 times 14 times 13 times 12 times 11 factorial. That's a little bit more common to see that. And then we just cancel out the factorials like that. Okay, example 2 is next. 5 runners need to be arranged in 5 lanes for a race so that there's a runner in each lane. How many unique ways are there to arrange the runners in 5 lanes? So this says unique ways. That's our key indicator that we're using permutations for this. So for the total, there are 5 for our total, and then there are 5 runners that are being arranged. So in this case, n is 5 and r is 5. So we would write this 5p5, and that if we use our formula again, n factorial is 5 factorial over 5 minus 5 factorial. That equals 5 factorial over 0 factorial. Now 0 factorial, this is also very important to know that 0 factorial is equal to 1. It is not equal to 0, it's equal to 1. So 5 factorial, again, that's 5 times 4 times 3 times 2 times 1. And there is a factorial button on your calculator. When you're typing this into a calculator on the computer, you can always just write the exclamation point. It should give you the factorial answer. And so our final answer is going to be 120. So there's 120 different ways to arrange the 5 different runners in the 5 lanes. Okay. Next example, Amara needs to create a special tasting menu in her restaurant. She needs to select 4 dishes from 7 available dishes and put them in a sequence. How many unique ways are there to arrange 4 of the 7 dishes? So n is 7. We have 7 dishes total, and we're selecting 4. So this is going to be for NPR is equal to 7 factorial over 7 minus 4 factorial, which is 7 factorial over 3 factorial. And that's 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. And when we multiply all that out, we get 840. Let's take a look at how we would solve this on the calculator real quick here. Just so that you know how to use the calculator for some of these problems where maybe it's a little time consuming to do the to do all the math and write all this out. So because when we have to do multiple within one single problem, it can be a little time consuming. So let's type this same amount in here. So we're doing 7 choose 4, and I should have written that here. Let me write that here. 7p4. All right. So we're going to go to function on the scientific calculator. This is from desmos.com/scientific. And then we're going to click NPR, and then you just type 7, 4, and it'll give you the same answer of 840. So that's how you do that on the calculator. All right, one more here where we have to filter out extraneous information. It says, what's an appropriate value of N and R? Pierre's favorite singer has made 6 albums containing 75 songs in total. She wants to make a playlist of 10 of those songs, and she won't repeat one of the 75 songs. What is N and R? So N is the total. We have 75 songs in total, and R is how many songs we're choosing. We're just choosing 10 of those songs. And this problem, again, just wants you to write what those values are there. All right, on to combinations next. So combinations is used when we're selecting items and the order doesn't matter. So in this previous example with the songs, they wanted their songs to play in a certain order, but in the combinations, in anything to do with combinations, order does not matter. That means that choosing the same items in a different order still only counts as one outcome. So if you were, say, trying to choose a pet and you had to choose between a cat, a dog, or a fish, and you had to choose two of these outcomes, you could say you could choose a cat and then a dog, or a dog and then a cat. If this was permutations, we would say that that's two outcomes. If this was combinations, we would say that, well, the order doesn't matter. So a cat and a dog or a dog and a cat is still the same outcome. So that's just one outcome. Another way that helps me to remember the difference between permutations and combinations is to think about a combination lock. A combination lock is actually a permutation because when you put in the combination for your lock, the order of the number matters. If you enter in those numbers out of order, the lock won't open. So instead of calling this a combination lock, maybe a more appropriate name might be a permutation lock because technically that's what a combination lock is. And that's usually what helps me to remember the difference between permutations and combinations is that a combination lock uh, isn't is not a combination in terms of combinations or permutations. So permutations, order matters. Combinations, order does not matter. All right. So the, let me erase this part of the example here. The formula for combinations is very similar to permutations, but it is different. We write it NCR, which is in N choose R. N is still a total, and R is still the amount that we're choosing or selecting. And that's equal to N factorial over R factorial times N minus R factorial. So all that's been added to this formula is that R factorial. All right, now let's take a look at our first example on here. It says a basketball team has 10 players. Before each game, the coach picks two of those players to carry the team's water jug. How many different groups of two players can the coach pick? So in this one, n equals 10. And he's choosing two. And we would read this as 10 choose two. So we would write it 10 choose two. And that's 10 factorial over 2 factorial times 10 minus 2 factorial. It's 10 factorial over 2 factorial times 8 factorial. I'm just going to write parentheses just because I've got the factorial symbol there. It can be, just don't want any confusion there. So now this is 10 times 9 times 8 factorial over 2 factorial times 8 factorial. And we can just cancel out these 8 factorials. Now we're left with 90 over, and then 2 factorial is just 2 times 1, which is 2. And we should get 45. All right, let's try another combinations problem. Monique wants to check out as many books by her favorite author as possible. She can check out 3 books at a time from her library, where there are 6 books available written by her favorite author. How many different sets of 3 of these books can Monique choose? So n equals 6. There's 6 total to choose from, and she's going to select 3. So this is 6, choose 3. That's 6 factorial over 3 factorial times 6 minus 3 factorial. That's 6 times 5 times 4 times 3 factorial over 3 factorial times 3 factorial. That's going to cancel one of those 3 factorials on the top and bottom there. Now we're left with, let's see here. Make sure I'm doing this correctly. This is 6 times 5 times 4. That's equal to 120 over 3 factorials, 3 times 2 times 1, which is 120 over 6. And that gives us 20. All right. Here's another one where we're given information in a table. Raymond he's competing on a game show. He needs to choose 4 materials from the list below and use those materials to create a craft. So we have this list of materials. There's 9 materials here. So n equals 9. And he's going to choose 4 materials. So R equals 4. And it says how many different sets of materials can he choose? So this one is 9, choose 4. And this is going to be 9 factorial over 4 factorial times 9 minus 4 factorial. It's 9 factorial over 4 factorial times 5 factorial. 9 times 8 times 7 times 6 times 5 factorial over 4 factorial times 5 factorial. Cross those out. And now we have 3024 over 4 factorials, 4 times 3 times 2. I'm just going to write that out. 4 times 3 times 2 times 1. 3024 over 4 times 3 is 12 times 2 gives us 24. And our final answer for 9 choose 4 is 126. Okay, so that's how to calculate combinations. Next, we're going to look at permutations and combinations with overcounting. And this is very similar to subtracting the intersection with probability. In fact, it's almost the same idea where we're going to count 2 different things, but we want to subtract their intersection because we can't double count things. And that's what overcounting really is. So let me see here. Okay, so let's look at this first example. It says how many numbers between 1 and 100 are divisible by 4 or 5? So first we have to figure out how many numbers are divisible by 4. And if we want to figure out the multiples of 4, we could write 4, 8, 12, 16, and we could write our list all the way to 100. But a shorter version of that would be we're going to start at 100 and divide by 4. That gives us 25. That tells us that there's 25 of these numbers. So there's 25 multiples of 4 that go up to 100. So let's hold that number for now. We'll call that step 1. For step 2, we want to find the multiples of 5. And you could write the list of this again if you wanted to, but shortcut is 100 divided by 5 gives us 20. Now you might be thinking 25 plus 20 is 45. That's our answer. You're close if you think that's our answer, but that's not quite our answer. So what we have to do is subtract the overlap. And the overlap happens. Let's see if we can find what the overlap is. So if we write our multiples of 4, I'm going to write this out to 20, and our multiples of 5, the least common multiple of 4 and 5 is 20. This is our first number that is an overlap number. So now if we were to count by 20s, we would get an overlap number each time. And this list was very short, so we can just count what that is. And that's 5 outcomes where it's counted twice. But another way to write that is there's 100 numbers, and divide that by 20, which is the least common multiple of those numbers, and that also gives us 5. So this is the part that we're subtracting because it's been counted twice. So now we're going to combine all of this. How many numbers between 1 and 100 are divisible by 4 or 5? Well, there's 25 4s plus 20 5s, and then we're subtracting 5 of those because 5 of them are duplicates. And so we should get 40 numbers for our final answer. All right, let's look at a different one without numbers. So this time it says we have these reindeer that we have to put in order. Jebediah, Lancer, Ezekiel, Glupin, and Blupin. And we have to put them in this single file line to pull a sleigh. Lancer and Ezekiel are best friends, so you have to put them next to each other or they won't fly. All right. So this is almost like the fundamental counting principle by itself, except we're dealing with the Lancer and Ezekiel part where they have to be together. So the first thing we're going to do is we're going to arrange these 1, 2, 3. Let's see, 1, 2, 3, 4, 5. 1, 2. All right, so we're going to arrange these 4 objects. There's 5 reindeer, but there's actually 4 objects because Lancer and Ezekiel, we're going to treat that as one group by itself. So we're going to arrange these 4 objects 4 factorial ways. And that's 24 different arrangements. Okay, now we want to arrange Lancer and Ezekiel inside what I'll call their block. So for Lancer and Ezekiel, it can either be Lancer and Ezekiel, or it could be Ezekiel and Lancer. These reindeer are all pulling the sleigh in a specific order in a straight line. So those are our only 2 options for those. We would write that as 2 factorial ways, which just so happens also just equal to 2 times 1 gives us 2 arrangements. All right, so we want to subtract, or we want to get rid of any duplicate arrangements. So To apply the fundamental counting principle here, it says to multiply all the possibilities to find the number of ways something can be arranged. Uh, Actually, we're not getting rid of anything. We're putting all of the possibilities. So we're putting this possibility and that possibility there. So this is more of a, I can think of it maybe as a combinations problem, uh, or excuse me, a permutations problem. So we're gonna multiply 4 factorial times 2 factorial, and that's going to give us 48 arrangements. All right. I think that was probably one of the tougher ones. Let's go to the next example here with when they give us a word and they want us to figure out how many unique ways there are to arrange letters in a word. So we want to know how many unique ways there are to arrange the letters in the word pretty. So our first step, there's 6 letters. So 6 factorial gives us 720. There's 2 T's. There's T1 and there's T2. So we'll call that T1 and that's T2. We have to put subscripts because we're going to call both of those T's a letter T. It wouldn't make sense to call them any other letter. So that's why we put the subscripts there. Okay, we can arrange the T's. We can write them as T1, then T2, or we can write it as 2T2, then T1. So there's 2 factorial ways, or 2 ways that we can arrange these. In this case, we want to know how we can arrange the letters in the word pretty. So it's still going to spell the word pretty. So in this case, we're not just going to use the fundamental counting principle and multiply. We're going to divide by 2 factorial. So for our final answer, we're going to write 6 factorial divided by 2 factorial. And this is 720 divided by 2, or 360 ways to arrange the word pretty. If a letter repeats itself 3 times, we would divide by 3 factorial. If one letter repeats itself, let's look at another example for this one. So if we had another word, banana, and we ask the same question, how many ways are there to arrange the letters in this word, banana? In this word, we have an A repeating itself 3 times and an N repeating itself 2 times. We still have 6 letters, so this would be 6 factorial divided by, and because we have the A repeating 3 times, we're going to divide by 3 factorial, and we have the N repeating 2 times, we're going to say times 2 factorial. So that's just how we would solve a different problem if we had letters repeating with more than just one letter. All right. The next section is on probability with permutations and combinations. And this section, we have to identify if we're dealing with a combination or if we're dealing with a permutation. So that's the first thing we have to do. And then we have to identify what the probability is. Is there just one possible outcome, or are there more than one possible outcomes? And how do we write that possibility in terms of a permutation or a combination? So let's look at our first example. It says a pizza restaurant is offering a special price on pizzas with 2 toppings. They offer the toppings below. And those are all the toppings that we have to choose from. It looks like we have 8 toppings altogether. So n equals 8 and r equals 2. But our first question is this a combination or a permutation? So if we're talking about toppings on a pizza, the order should not matter because they're just pizza toppings. It doesn't matter what order that you put them on the pizza. They're going to be on the pizza regardless of the order. So this one is a combination. Say order does not matter. Now we're going to write the combination formula. So this is NCR, which is 8, choose 2. And this is the total amount of topping combinations that they could choose from. Okay, and then now we're talking about probability. Total goes on the denominator of our fraction. So now we know that this is our denominator. You might be able to see how to eliminate some of these answer choices so far, just based on the multiple choice. Okay, now we want to calculate the probability that Rosa's mom can choose sausage and onion as a topping. So to calculate that probability, the order does not matter. That means that sausage and onion is the same thing as onion and sausage. So there's only one way to choose sausage and onion as a topping. So now we're going to write the probability expression. And that's 1 over 8, choose 2. Okay. This next example is a little bit tougher. This next example, we don't have a table and we have to figure out if it's permutation or combinations. So this is about a list of people who are going to be selected to either be president, vice president, secretary, or treasurer. We want to know the probability that Nia is chosen as president. So our first question is this a combination or is this a permutation? Now let's think about a couple of scenarios. We'll think about scenario A, and we'll say Nia is the president, and some other student will randomly give them a name. We'll say, and Alex is the vice president. And scenario B, we'll say Nia is the vice president, and we'll call Alex the president. So we need to ask ourselves, does switching these assignments create a different outcome for scenario A and scenario B? Which means if we switch the order of these things, does that mean that scenario A is equal to scenario B? If scenario A equals scenario B, then it's a combination. If A is not equal to B, then this is a permutation. And in this case, these A and B, these are two different outcomes. Nia is not the president in scenario B. So A is not equal to B, and this is a permutation. So that's step one, is figuring out, is this a permutation or a combination? And you can always write out the scenarios like this If you're ever not sure, you can ask yourself, well, are these two things equal or are they not equal? All right, now let's identify N and R. So there are 24 students in class. N equals 24 and R equals 4. So now this is for N, P, R. This is 24, P, 4. And this is how many total possible arrangements there are. That's our total possible arrangements. Okay, now to step 3, which I thought was the toughest part about this problem when I was first reading it. So we want to determine the probability expression here. It says, uh, so to determine the probability expression, our last example, we had one way that these items could be chosen. But there's more than just there might be more than just one way that Nia can be chosen as the president. So our probability that Nia is president is equal to the number of arrangements that Nia is president, with Nia as president, with Nia as president, divided by the total possible arrangements, which we found out already is 24 P4. So now we can automatically cross out B. That helps us a little bit there. Okay, so the number of arrangements with Nia as president is saying that since Nia is already president, we now have to figure out the other people being selected for the other roles. So there's now 23 students left when Nia is president. So now there would be, for the numerator, just going to write for the numerator, now N equals 23. And there was president, vice president, secretary, and treasurer left over. Or those were the 4 roles, and we have 3 roles remaining. So R equals 3 in this case. Okay, so when Nia is president, we have 23 students left, and we have 3 more roles to choose. So our final probability statement is going to be 23P3 over 24P4. And when we simplify that, that just so happens to be 1 out of 24. And you probably knew that from the very beginning. The probability that she's chosen as president is 1 over 24. Nia is 1 out of 24 students. But this does simplify to 1 over 24. So you can check this on your calculator. That's another way that you can confirm that this is true by looking at what is the probability just without permutations and combinations. And then we'll see if that matches what those values are. So if you get stuck on a problem like that and you have multiple choice, you can certainly solve it that way, or you can check your answer that way if you need to. Okay, there's a couple more. Looks like we have 2 more example problems left. Sophie claims to be a tasting expert to test her abilities. Someone bakes Sophie a cake using 3 of the following ingredients. So it looks like we have 6 ingredients total. Actually, first let's figure out if we need combinations or permutations. It says, what's the probability that Sophie correctly identifies the set of 3 ingredients in the cake? So we're talking about ingredients. Um, Sometimes when we're baking or cooking something, the order matters, but in this case, we're just talking about ingredients being added. So in this case, we're just talking about combinations. Okay, so order does not matter. So now we know we have an NCR problem to think about for what our denominator is of our total. So N is going to be, we have six ingredients total, and we're excuse me, six ingredients. N is six, and R, we're choosing three. So this is six, choose three, and that equals 20. Again, you can check that on the calculator, or you can write out the formula if you need to practice that a little bit more. So this is going to be the total, and that goes on our denominator. Okay, and the probability that she correctly identifies the set of three ingredients in the cake, there's only one way for the three ingredients to be properly identified. So if we had, let's just say, for example, the ingredients, let's say the ingredients were vanilla, salt, and ginger. There's only one way for those to be correct, even if we got the ingredients that were salt, ginger, vanilla. That's the same thing. So because that's the same thing, we just have one possibility of selecting all three of the right ingredients. So there is the probability of all three correct is one possibility out of 20 possibilities. So B is our answer for this one. All right, let's take a look at one more problem together. I think this last problem is a good example because it talks about a passcode. And we talked earlier in our lesson about how combinations on a combination lock is actually a permutation. So that helps us right away to see this is a passcode to enter a building for this problem here. And so we automatically are going to know now that this is a permutation because passcodes, you have to put in the passcode in the correct order. If you don't, then it will be the wrong passcode, even if it's the right numbers. So this passcode in the building is a 4-digit passcode. You can use numbers 0 through 9, and repeated digits are not allowed. It says, suppose someone doesn't know the passcode and randomly guesses a sequence of 4 digits. So first, let's figure out what n is. Our total is going to be 10. So 1 through 9, and then 0 would be our 10th. So that's our total, and we're choosing 4. We're selecting 4 digits. Now this is a permutation. Maybe I shouldn't have said choosing 4. So this would be 10p4. So now to find our total possibilities, we would just do 10p4. But it looks like all of our answers here are 10 are in terms of permutations or combinations in our answer. So it looks like we don't have to solve for what 10p4 is. So that might save us a step. So we can cross out the combination possibility because we know this is permutations here. There's only one correct passcode. So there's only one possibility out of 10p4 possibilities. And that's a little bit of a simpler example, but I did want to end there because I wanted to tie back to how a password or a combination lock is permutations where the order matters. hopefully that helps you to remember the difference between combinations and permutations. All right, so that is everything on the combinations and permutations and the probability lesson with combinations and permutations.